Hello and welcome to Module 0 of our Data Science and Machine Learning course from Shift SC. In this module, we're just going to be talking about data science and some of the basics that you need to know before you get into machine learning.
Hello, I'm Rida. I'm a second year currently studying computer engineering and computer science.
My name's Ryan. I'm also a second year currently studying computer engineering and computer science.
All right, so in this module, we're going to be covering the basics of data science, what it really is, what is its significance in the ML world. Then we go into the ethics of data. Then we're going to learn how to clean some data sets, then data visualizations, and then data distributions.
So before we begin, we need to ask ourselves a very fundamental question, is what is data science? At its core, data science is, well, the science of data. It's a field concerned with extracting useful information from messy and unstructured data that would be collected from the real world. For example, a lot of companies will mine data or use data in order to do things like advertising or finance. It's also very often used in medicine for diagnostics and triage. So it eventually becomes an interdisciplinary field combining statistics, computer science, and domain-specific expertise to deliver improved services to the general public.
So before we actually get into how to manage the data that we have, let's look into the ethics of collecting this data. So there's 6 key principles that you want to keep in mind whenever you're dealing with data from a wide base of users or just general audience, general public. So the first one is consent. Before you even get started, you want to get permission from the people you're collecting the data, because in the end, it's their private information and you want to make sure you're handling it well, with care. The second is transparency. So with this, you want to explain the process. How are you collecting the data? Who are you collecting it from? And where is it going? You want to be as clear throughout the entire process what's happening with the data you're collecting. Third is anonymization. So you don't want any identifying information, and you want to make sure that the identities of the people you're collecting data from is not disclosed throughout any of this process. Then we have sampling. So you want to make sure that the samples that you collect accurately represent a population. So for example, if you want to get an accurate representation of students in middle school, then you want to make sure you're covering a wide variety of bases and really making sure that all populations are represented within this sample. Finally, we have compliance and quality. So with compliance, you want to make sure you're just following the laws. There's already a lot of rules and regulations in place when it comes to data handling, so just making sure you're abiding by these laws. And then with quality, the higher quality your data is, the better the results of your model are. So just make sure at every point in time that you're following best practices for data collection.
To give you an example of why this is important, it's important to highlight in the machine learning space that models learn on data. The models we create use insights that are ultimately extracted from the data set, whether that be some kind of neural network or even as simple as a regression or just a prediction. These insights can be useful and generalized well, but what if the data set itself is bad? If the data set itself is bad, what ends up happening is that the model gets a bad insight into the world. If you look at the photo on the right, Bloomberg did an analysis of a lot of stable diffusion models, which are just image generation models, and how they tend to perpetuate criminal and racial stereotypes. If you look at the keywords that were asked to be generated, there are given the distributions of skin tones for those images, as well as the average face of the people in those generated images. And as you can see, there's a very clear racial bias in how the model sees these people or these individuals. So as a result, it's very important that we really focus on creating a high-quality data set. A simpler example is, suppose we have a data set of 1,000 people, of which 990 live in Seattle and 10 live in Los Angeles. Suppose we have now, a data set, but suppose now we have a model M that predicts which city a person lives in, and we train model M based on that data set of 1,000 people. In this scenario, if the model only ever outputs Seattle, it would achieve a 99% accuracy on this data set. So the question is this a good model? It has 99% accuracy, but ultimately, not everyone lives in Seattle, so it's not a great model. The question then becomes, how do we improve the model in a case like this? And this comes down to a process of dataset curation. Dataset curation describes the act of collecting, annotating, and filtering the content of a dataset to avoid the so-called garbage in, garbage out problem that a lot of models fall victim to. The idea being that if the dataset or the insights that you give the model from your dataset are already bad, then whatever outputs the model has are also going to be bad. And this is why data science matters. In the previous example, for example, we could have included more individuals who lived in Los Angeles to even out the distribution. We could have also included less people who lived in Seattle, but that would also change things up about how we can generalize our inferences and would just overall reduce the size of our data set. And this kind of comes back to the idea of representative sampling that we were talking about earlier.
All right, so without further ado, now that we know the basics of data collection and data set curation, let's get into manipulating data. And with that, we have these notebooks, so we're going to lead you through and see how you can actually start your problem sets. Let's look at some of the key terms you guys will need to know. So starting with Google Colab, this is basically the platform that you will be using to host all of the problem sets, and it's a document where you can actually run, edit, and share Python code all on your own browser. And then with that, we also have some Python libraries that you guys will need to be using, starting off with Pandas. Pandas is a very common Python library that's used for data manipulation and exploration. It has lots of useful methods that you can use to both analyze and manipulate data, and overall just explore these data sets before you actually start using them for machine learning. With that, we also have scikit-learn. Scikit-learn is typically used in machine learning contexts, a very helpful library with lots of classic functions that you can use. In our case, we will be using scikit-learn to actually download the data set that we will be exploring. Then lastly, we have matplotlib. Matplotlib is a Python library that you can use to create interactive and interesting visualizations. So once again, there's lots of functions that you can use to customize and explore different visualizations of different data sets. We also have data frames. So data frames are basically Python's way of storing data. It's a data structure that organizes all of the information in a typical data set into rows and columns. So we will be looking at the iris data set. So you can think of one data frame as just this field of irises. From there, we have what each row actually means. A row is basically one entry or one singular iris in the overall data set. Then finally, we have columns or the features of the data. So this is each attribute of a data entry. So in the iris data set, we will see things like either iris petal length or iris sepal width, and just think of it as just main features, main key points of each data attribute. So these are what your notebooks basically look like. They're split into different segments, going through loading the data, cleaning the data, visualizing the data, and then finally trying some exploration on your own. So basically just run through these step by step. There's lots of other helpful information and resources that we would highly recommend you to read through. So let's start off with actually acquiring the iris data set. So for this part, we want to load it in. And before we can even begin doing all of that and using the functions, we want to import the libraries that we will be using. So just like I introduced, we have the pandas library. You want to use a quick nickname, import pandas as PD. And then once again, that will be the library we use to actually call the functions that are going to be used to manipulate the data. And then we also want to import our actual data set. So with that, we have the scikit-learn library. So from sklearn.datasets, you want to load specifically the iris data set. And if you look into the documentation, there's lots of cool data sets that you can look into, but for our case, we're going to be using the iris. So now that we have that in, we once again want to load in the iris as a variable, and this will basically hold the data set straight from the sklearn library. Then we want to use the data frame method that I talked about earlier, and to do that, you call pandas, their data frame function, and with that, you add in the parameters, so one with the iris variable we just created, the data for that, and then we want to define, like I said, what each column or feature will look like, and for that, we also will refer back to the iris variable that we created, and then just use iris.featureNames. So what this step did, finally, we have to add one more column, which is species. So the way that the iris data frame works, it stores in sepal length, sepal width, petal length, and petal width. But there's actually one more attribute, is that all of the irises have different species. And to do that, we want to create a new column. So just calling your data frame, refer to it as an array object. We create a new column, and then we just set iris.target. And target is an attribute of this iris data set that basically stores these different species names. So yeah, that's how we load in the data. And then finally, we can figure out what's actually within the data set by doing print.dataframe.head. If you run that. Then here we have our data set. We have all of the first 5 rows of our overall data set. You can see the different features, sepal length, sepal width, petal width, and then also the new column that we created, which is the species column. So right now you will see numbers. They're not actually the names of the data set, but each number corresponds to different iris species, just like Setosa, versicolor, and virginica. So we'll be using that to further manipulate and filter out different attributes of this data. So yeah, that was the step to load the data, and we can now move on to cleaning data.
So now coming into the notebook, we want to do some things with just examining and cleaning our data set. We'll start off with just learning a bit more about the data. For example, we can do things like get the species counts, which is just the number of different species that there are in the data frame. So you can see I can index into the data frame by using a specific column name, and then call value counts on that as that returns a sequence for that specific column. And then we'll print that out to show it to us once we run the cell. Now, another thing we can do is also sort the data. Having sorted data is really nice for a variety of things, such as searching, mostly searching. But in any case, as you can see, we can call sort values on the data frame and then pass the by argument in order to tell it which column on which to sort. So we'll use the values in the petal length CM column in order to sort the data frame rows. And then very quickly, we'll just write some print statements for that. My bad, I exited the I exited the parentheses, whatever. And then we'll just quickly print the head and the tail. And then now what we might want to do is say filter out the data to only include, say, irises with a petal length greater than 6. This is something you can do in Pandas with the inbuilt functionality, and you don't have to do it yourself. So, for example, what Pandas allows us to do is pass in a Boolean expression or comparison into the indexing kind of function, which is just the square brackets. And then using that, we can actually just ask it to isolate the specific rows where the petal length CM is greater than 6. And that'll be returned into our new data frame. So just quickly print that out. And then just print out the head as well. Now what we might want to do, for example, is clean out the data and only display the rows where the species is Setosa and display some petal results. So we know this for the iris dataset that the Setosa species is equal to 0. So first what we can do is isolate that species using, again, the same kind of Boolean comparison in the index. Then what we can do is index into that new data frame for the specific list of, and you do have to pass it as a list, of columns that we actually want out of this data frame. In this case, we want the petal length, petal width, and the species. So we'll just quickly put that in. And then just quickly print all this out. So just copy paste because then change some things. Just change this name really quickly. And then we'll just print the head and then run the cell. And so as you can see, it tells us that there's 50 of each species. We have our sorted data sorted on petal length CM. You can see in what appears to be ascending order. Continuing onwards, we also have our clean data here, as in our filter data as well. So that's, of course, all the functionality, some of the important functionality, of course, that you can get out of Pandas. Of course, there's a lot more, and you should definitely refer to the documentation that we have here. We also have a set of exercises for you to do yourself in terms of cleaning the data and using the Pandas functionality for cleaning it. So coming back from the notebook, the important thing here is that representation in the dataset matters. A model, again, is only good if the data is good, and sorting and cleaning the data can vastly improve the quality of a dataset. There are other things you can do, such as like outlier removal, as well as altering the data set, shifting it, transforming it if you do want to do some sort of augmentation to it, or perhaps want to move it into, just a kind of better value range for the work that you're doing. The iris dataset is a really good example of a strong dataset because it has an equal representation of its 3 species. But an important question to have is that, are these all of the species of iris that exist? And the answer is no. These are just 3 different examples that are in a small little demo dataset for you guys to use in learning about pandas, matplotlib, etc. So now we're going to move on to the visualization section of the notebook. So coming to the notebook for data visualization, we're going to be using a library called matplotlib. Matplotlib is a very powerful Python library that's used for just plotting. It's in the name, pyplot. So we import it under the alias plt. We'll call everything that we want on plt, and everything that we need from matplotlib will be coming from the name plt. So to start, we'll just start with a scatter plot of petal length and petal width. Pretty simple. We will use the plt.scatter function. This essentially just creates a scatter plot using the given two series. I don't know why I put quotes there. But yeah, it's essentially the same thing, just index into the into each of the data frame columns using their names. And then, once we type all this out, species. And this, of course, this keyword argument C is just used for the color. So we have, I think, what is our, one of these is the X value. I believe this is the X value, and then this should be the Y value. And then we can continue to add features onto our graph, such as X label. Or, no, I got it backwards, actually, my bad. The first is the X value, and then the second is the Y value. So we'll just quickly add some labels for each of these axes based on the columns we're using. And we can directly call all of these on PLT and add it to just a kind of main plot. Sorry. Give it a title. And then finally, all we need to do to show it is plt.show. And when we run the cell, as you can see, it shows us our plot of petal length by petal width. And of course, also colored by the species of the irises that correspond to the data points that we passed in by index. Now, if we want to, say, plot a histogram of species and frequency, we will, for this one, we're going to use NumPy, or, sorry, not just yet. Yeah, sorry. We are going to use NumPy for just some random stuff, essentially just literally random sampling. So what we're going to do is just use np.random.choice in order to create a list of just really a bunch of different indices from the data frame. And of course, this np.random.choice will create a list of a set of unique elements. So there won't be any overlapping indices, and we'll get 50 randomly selected elements from the data frame. The reason we're doing this, of course, and this is something you can or cannot, or you do or don't need to really know. It's not entirely necessary. But the reason that we do this is so that we can kind of disrupt the otherwise equal distribution of species that we have in the iris dataset. As we've spoken about, it's a perfect 50-50-50 split. So the issue is if it's a perfect 50-50-50 split and we plot it as a histogram with 3 bars, well, we just get a big rectangle, and that doesn't really tell us anything. So we'll just change things up for the sake of visualization. And then we will create our bins in the plt.hist function. This will just generate a histogram plot, add our information. I think, oh, my bad. I mixed this up. I really can't spell today. But yeah, then this should finish our histogram. We've added the information. We've made our histogram using plt.hist. And now we just plt.show. And there you go. You have a randomly sampled histogram that shows you the number of flowers per species. Of course, it's weirdly quantized. I'm not really sure why that is, but it's probably because the data frame itself is storing the species value as an integer rather than some kind of object. So hence you get this kind of weird nonsense. In any case, another important function to know is the plt.figure. What is the plt.figure? It is a, well, the way that we use plt.show and plt.plot essentially puts it onto a main plot that's just directly on matplotlib. But if we do subplots instead, what we get is a secondary figure that we can then call, show, and add plots to in order to do our plots. So it's really good for plotting multiple things together as it generates like multiple sets of axes. In this case, we'll create one with 1 row and 2 columns, and then make the figure size. And then we'll just pass in a tuple for figure size, so 10 by 10, just the visual size of it. So then we'll start off with ax 0, and on ax 0, let's just say that we want to plot petal width and petal length. So we'll do ax0.scatter. I think one of the plots that we've already done, by the way. Petal length as a secondary, yeah. df petal width c equals df species. Thank you, autofill. Yes. X0.set. In this case, we do also have to use set x label as opposed to just x label because we are working with an axes object. Yes. Okay. And then in this case, we're just also going to set the y label. And then the final thing we want to do is just set the title. And we'll just set it to petal length, petal width. And then now what we will want to do next is we're going to create another plot, very similar. In this case, though, we're just going to use ax1, or index 1. And this is just the second set of axes that we have in our figure. Now, of course, if we were to include more rows, then this would become a two-dimensional list. So we'd have to index into it once to get into a row, and then index into it again to get to a column. In this case, because we only have one row, we only need to index into it once, which is very convenient. Now what we're going to do is plot the same things, but for sepal length and petal length. So just change up some words. So many typos today. Yeah, and then finally what we want to do is call show on the figure, and this should plot our figure with two graphs. There we are. And these, of course, are two different graphs with different kinds of data. This is especially useful if you have a lot of different relationships that you want to plot in the same go. For example, if you have multiple metrics that you're using to evaluate something, or just a lot of different data fields that you want to see the correlation between in your data set, this is very useful. With that being said, we also have the matplotlib documentation linked. You should definitely refer to this for more information. And we have some exercises as well for you to do yourself, including plotting functions, as well as plotting some of the stuff from the iris dataset. Coming back from the visualization section of the notebook, I think there are a few things that we need to think about, especially when it comes to ethical use of visualizations and correct use of visualizations. If you examine the graph that's currently on the slide, it seems like there's a significant difference between each of the different car companies. But check the y-axis again. The y-axis only ranges from 95% to 100%. So in actuality, what the graph should look like is something like this. And in a graph like this, there's not actually that much of a difference. But in the previous representation, we were able to convince you that there actually was a significant difference. So obviously, there's a lot of issues about how we display data and how we visualize it.
This actually leads into our key concept, visualization ethics. So when it comes to data, data tells a story. Every single visualization that you make has impact. I mean, just look at advertisers. There's always a lot of charts and graphs represented for you, but you have to be wary, are they actually representative of the story they're trying to tell? Just look at this graph, for example. As you can see, all of the figures are only there to represent height. But because of the differences in width, you see Latvia is represented as deceptively large, disproportionately, and at the bottom we have India, very tiny figure, because of the different scaling when it comes to the width, you see a misrepresentation of what the data is actually trying to tell. So with that, we have some key concepts you want to keep in mind. So honest data presentation is a huge responsibility. So these are some common poor practices that you want to avoid, whether you realize it or not. The first of this is scale distribution. So we saw that in the previous example with the cars. Since we had the scale starting at a lot higher than it initially was set to, it made it look like the scale was representing a huge proportion. If you look at this graph as well, if you were to make the scale way larger, it would end up making all of the data points at a very small layer, and it would make it look like there is no difference between them. So some simple changes like scale distribution actually ends up making a big impact on the story that's being told by a visualization. We also have 3D distortion. So similar to expanding the width, some people actually expand the 3D aspects of a graph, which makes the bar once again look deceptively larger than it actually is meant to be. We also have color usage, things like red, green, these all invoke certain emotions in people's minds. So even something as simple as that can lead to telling a different story than what you actually want to represent honestly. Then finally, cherry picking. Cherry picking is very common where many researchers, data scientists, they will use data points that are more relevant to the conclusion they're trying to make. So make sure you avoid doing that. Any outliers is still a part of the overall story you're trying to tell. And then finally, out of context data. So when you see certain graphs, you want to make sure you're accurately representing what they are, because sometimes taking things out of a certain context will end up painting a different story. So now that we've looked at all kinds of ways you can manipulate data in Python, let's take a step back and then just look at what data represents overall. One way to do that is looking at the distribution of your data. So when it comes to data, there's a lot of common distributions that are already used and often found naturally in our world. So distribution of data basically reports on just how well the data is spread out. So metrics like standard deviation, mean, all of these tell stories about the data and just overall are good metrics to figure out what the overall spread, what the overall variance is going to look like. So we look at data from certain populations, and with that we can observe different distributions. Some of the most common ones that you would see in probability or just your overall statistics classes are things like normal distribution, geometric distribution, binomial, and Poisson. So on the right, you can see two of these images. We have a normal distribution at the top. This one's very naturally found in populations when taking data from a very large set of people. You will find that a normal distribution is often what these values map to. Then we also have a geometric distribution pictured at the bottom. So all of these are different distributions that you're likely to find when collecting data from a large population. So let's look back to the visualization that you actually just created. We have the petal length versus petal width plot. And as you can see, we can add a line of best fit to accurately represent all of these data points together. And what you see is a linear relationship starts to be formed. Data can be mapped out using different functions, but this specific example can be mapped out using y equals mx plus b. So think of that equation. If you change things like m, different slopes, you can make it steeper, shallower, things like that. You also have the b value. That's going to control where the actual line plot starts in the overall scheme of things. So as you can see, using this formula, we can actually start to make predictions. So we have all these points plotted out here, but let's say we wanted to look at a petal length of x equals 2.5 centimeters. So if we do that, we can actually go into the graph by going to x equals 2.5 and then seeing what y value corresponds to that. We can get a pretty accurate guess of what the petal width is going to be. So things like this, all of these linear equations, all of these formulas, they actually help us make predictions. And this right here is the basis of machine learning. All of this data is going to end up helping us make a model that can accurately help us predict values that are uncertain. So with that being said, we need to ask, can all data actually be mapped to a function? And the answer to that is that there's a lot of different variations and a lot of outliers you're going to see, but for the most part, data is pretty accurately represented by machine learning models, and we can get some really good predictors by just using these types of fits. So if we look at these two examples over here, we also have things like nonlinear relationships. The previous one was y equals mx plus b, but what happens if the data ends up being not linear? Like here we can clearly see that there's a lot of different complexities and different features that we need to see for the data. And then after that, let's say we weren't just looking at petal width. Let's say we were also looking at stem length or leaf length. How do these factors also contribute to the overall result or the petal width factor that we're looking into? And with that, the graphs start to get a little bit more complex, as you can see over here, but all of these multiple input parameters will still map to an overall function, and these are the key ideas that you're going to need to know going into the future lessons. And next time, we will dive into that more with machine learning. So in this module, we covered the basics of data science, everything that you need to know about data collection, its ethics, and then we looked at Python functions to actually clean up a data set and visualize it. And then we wrapped up looking at data distributions and how this is going to eventually play into machine learning.
To end, we wanted to thank you for doing Module 0, and we hope to see you again for Module 1, where we'll be doing an intro to machine learning.